Hi everyone, my name is Michał Kulczykowski. I'm a senior machine learning engineer here at DeepSense, and today I will be talking about JEPA and world models, the path to AGI. This is my short agenda. I will start with explaining what world models are and why are they important. I will mention a brief history of the world models and what is the most recent development in that area. I will move to JEPA, what it is, how do we train it, and then I will talk about few of the implementations of JEPA, mainly image-based, video-based, and LeJEPA. I will finish with criticism and conclusions. Recently, there is a lot of talk about how LLMs are the way to a way to achieve AGI through scaling of compute and data. But are they really that way? Here we have recent research from that takes LLM and trains it on orbits of solar system's planet. As we all know, the law of gravity can be seen here on the left side of the screen, and that's how it looks normally. But this LLM, when probed for the law, it uh, it it predicted, generated something very weird and confusing. The thing here on the middle. So what happened? So LLMs don't really, as we see, don't really possess good world models. And what are the world models? They're the physical representation of physical reality in an abstract way. They allow they allowed for prediction of interactions of objects in environment that allowed for the navigation and taking actions without complex sensory inputs. Why are they important? Because, as I mentioned, a lot of talk is about the scaling of LLMs that will lead to AGI. But some researchers like Yann LeCun mentioned that or postulate that we cannot achieve true AGI without internal world representations, in the same way as humans and animals have. So how do we acquire world models? Humans don't have a lot of labeled data. We interact from the very beginning with the environment through observations and actions. And as we can see, even small child before its 6 months of life already understand object permanence, and before 12 months of life understand gravity and conservation of moment. So what is really important here is that we acquire all this world reasoning using a massive self-supervision approach. So that's what we need for world models. World models are not a new concept. It's a concept that dates back to 1950s to neuroscience, but has been greatly researched in the realm of reinforcement learning throughout the years. But what is important is that the scaling of data and compute propelled the world models to the forefront of AI research. We have uh, we have such world models as the one that generate gaming scenes in DeepMind's Genie 2. We have 3D scene generation for World Labs, physical environment generation for training of autonomous vehicles from NVIDIA Cosmos, and video generation with OpenAI Sora. What connects all these models is that they are generative, meaning they think in pixel space. And thus we come to the JEPA, and what it is a predictive architecture. Here I will talk about what exactly is JEPA, how it's architectured, and how do we train it. So JEPA is energy-based models. That means it generates energy function that outputs a scalar value that maps region of low energy to data that is physically valid. Like for example, when I throw a ball through the window, it will fall down, and maps regions of high energy to data that is physically invalid. For example, if I throw a ball through the window, it will go up. And this energy function allows for multimodality, meaning that for one input, I can have multiple potential outputs, which means that, for example, when I throw a ball through the window, it can fall in numerous positions on the ground. What is very interesting about this approach is that inference is done through gradient descent when we look for the regions of the lowest energy. Here I will talk about architecture of JEPA. What is crucial is that both output and input is passed through encoders. That means that JEPA thinks in a representation space. The predictor takes the value of the input and takes into consideration latent variable z, which possesses information that is lacking in the context, and tries to predict from that the encoding of the output. And together they are trained using some loss on those encodings. This approach has one drawback, and that it can lead to collapse of the training. And that happens, for example, if the Z is so big that it can represent every possible input by bypassing any possible output bypassing the input, creating basically a flat energy surface. So how do we prevent the collapse? There are two approaches. One is a contrastive method, which tries to estimate the energy surface by probing the regions of low and high energy with positive and negative samples. This method has some drawbacks because it requires good negative samples. For example, dog versus wolf compared to dog versus car. This would be a good example, and may suffer from curse of dimensionality. So there is another approach called regularized method. Regularized method, they try to constrain the region of low energy, and they don't suffer from curse of dimensionality. So I will describe the first of the implementation of JEPA called I-JEPA, which is an image-based approach where then both encoders are usually vision transformers, where we pass in the context masked image, and predictor tries to predict in the representation space how the embeddings will look like and try to match them to a target encoder. The loss is a simple L2 distance loss for this example, and in order to prevent the collapse, there is this approach, the regularized approach, using the exponential moving average of the context waves in the target encoder. And as we can see, this is the reconstruction of the embeddings. Here on the left upper side, we can see a bird, and in the reconstructions, we can see that the model correctly recognizes that this is the back of the bird. Those reconstructions are not perfect because they don't need to be, and we can see that, but we can see that the model understands conceptually what's supposed to be in that place, just like a small child would. We can see something similar here on the right second row when the husky's dog leg is reconstructed correctly. Another approach is V-JEPA. This is JEPA trained on video frames. The approach is very similar. So encoders are also vision transformers. Predictor uses masks to predict the masked regions. This time the masking is consistent temporally to make it valid, and we again have exponential moving average of contact encoder weights to as a target weight, and we also have something called stop gradient. What is very interesting about vision JEPA is its approach to robotic arm. Here we have a model that has frozen both encoders, and only predictor is trained on 64 hours of robotic arm movements. This data is interleaved with arm's position, and the inference happens when we show to the model the image of the position of the robot, and robot tries to come up with various trajectories that can be used to achieve the position. The one with the lowest energy is picked. The robotic arm tries to move closer to the destination, and the replanning is repeated. So again, we pick another trajectory from the one of the lowest energy. And the last implementation is called LeJEPA. So LeJEPA is a very mathematical approach and tries to deal with the tricks and heuristics that I used up to this point. So all the exponential moving averages, predictors, and stop gradients are replaced with one SIGREG regularization that tries to force the embedding to look like isotropic Gaussian. So basically like a sphere in multiple dimensions. So JEPA itself is interesting approach, but there are some criticism of it. There is not enough good benchmarks that can prove that JEPA indeed is good world model, and it may suffer from the same problems of LLMs. And itself, JEPA is not a new concept, but amalgamation of already presented concepts, except for the LeJEPA, which introduces completely novel approach. In conclusion, world models are promising frontier in AGI. The concept is established, but the scaling of law of compute and data allow us to handle more complex and physical reality and reasoning. JEPA is one of the approach to this, but suffers from model collapse, and that makes it hard to train. While the progress in JEPA has been rapid, it's still an open question whether this approach really leads to a true world model. Thank you for listening, and any questions?